Hello everyone, welcome to another GIS lecture video, and in this lecture video I want to dig deep into the concept of universal transverse Mercator. Or UTM. So the goal of UTM is to provide a relatively localized coordinate system that gives you limited distortion for any given area, but it is only applicable for a specific area or a specific region of areas. And so the way that UTM works, right, if we imagine our diagram here that we've drawn so many times before, right, transverse Mercator means that we're dealing with a cylindrical projection that is drawn on its side, right? Again, this is just our definition here of a transverse Mercator projection. So with transverse, right, the idea was that you had what was called a central meridian. Right, and again, another term that we could use for central meridian is a standard line. Right, to use our terminology from distortion. That with universal transverse Mercator, right, we can pick our central meridian or our standard line. So what universal transverse Mercator does or aims to do, right, is it's actually a series of map projections, right? So universal transverse Mercator, I'm going to make a note here, right, is not one map projection. Right? It's actually 120. Map projections. And the reason that I say that is the way that UTM was designed was to take this central meridian every 6 degrees of longitude. Right? So what happened was, right, we have a central meridian at 0, right? Rotate, right? Because again, we can change aspect. Rotate the projection 6 degrees, create another one at 6 degrees. Right? Rotate again, create another one at 12 degrees. Continue this, right, until we get to, right, 174 degrees, right? Because if we go to 180, right, we're back at 0. So the idea here was that if we break, right, the Earth up into 6 degree, and this is by latitude, pieces, right? Which we call zones, right? So each zone is its own map projection, right? So we could have UTM1, right? So this would be zone 1, right? And this would correspond to 0 degrees to 6 degrees, right? Latitude. Then we have, right, UTM2, which is zone 2, right? That would be from 6 degrees to 12 degrees, right? And if we shove the standard line or the central meridian at 3 degrees and at 9 degrees, right, we've minimized that distance from the standard line in any direction. Because again, think back about distortion. What is distortion? Distortion is where the reference globe and the standard line, or the reference globe and the developable surfaces are different, and that distortion is minimized the closer you get to the standard line. So what UTM has done is it's just said, hey, let's break the Earth up into pieces called zones, each piece being approximately 6 degrees of latitude wide, stick the standard line down the center of it, so that at most you're 3 degrees away from the standard line. So your distortion should be pretty good. So we can take that one step further. Right, not only do we break them up into 6 degrees latitude, or sorry, that should say longitude. I am so sorry. Based on longitude. Based on longitude, right? 6 degrees based on longitude, right? We can also break them in half at the equator. Right? Break each zone in half at the equator. Right, so now, right, you have UTM 1S, meaning south zone 1, and UTM 1N, meaning north zone 1. Okay. Right? And so if we scroll down and we look at what this looks like pictorially for the entire world, right, you can see exactly what I was just talking about, right? That we have, right, the zones broken in half at the equator, right? This is north. This is south. Right, and then each one of these little slits here, this is a UTM zone. And again, right, these are 6 degrees of longitude wide. Right, so there's some wonkiness happening over here. This has more so to do with country boundaries and international dateline stuff. Just in terms of keeping certain countries wanting to be in the same UTM zones. It's not super important. Mostly what you're going to focus on most likely is going to be this block right here, which are the UTM zones for North America. So let's go ahead and quickly look at an example of the UTM zones in North America specifically, because that's going to probably be the most useful. Okay, so this is the UTM zones just for North America. You'll notice that California, we're at zone 10 north. Going over to parts of Maine are in 19 north. Okay, so this is definitely, you can Google this image from the USGS. This is definitely something to keep in your back pocket when you're dealing with spatial data, because being able to know what UTM zone to work with for the data that you're working in specifically is going to be extremely useful, right? Are you dealing with the eastern half of Michigan, you're going to be in 17. If you're dealing with the western half of Michigan, you're going to be in 16. If you're along that boundary, that's when you might want to start talking about something like state plane. Or again, we'll talk about this in future videos, the idea of reprojecting to be in a single UTM grid. But again, something useful to keep in your back pocket. What UTM zone should you be in based on where you're located? So what I want to wrap up this video talking about is measuring in UTM. Right. So let's assume for a second here. Right. So we're in a UTM zone, right? So this is the equator, right? This is our central meridian. Or to use the terminology of distortion, right, this is our standard line. Right, and so we know that from the zone boundary, if I can draw that a little bit cleaner, right, that from the zone boundary to the standard line is 3 degrees of longitude, right? But how do we actually measure in UTM? Well, like all projected coordinate systems, like I've said throughout the videos, right, projected coordinate systems use an X and a Y, right, an easting and a northing, right? But what does that actually mean in terms of UTM? Well, northing, right, Y, northing, is the distance north of the equator. If you were in the southern hemisphere, this would actually be a false northing because it would be the distance south of the equator, but it would be positive. So northing makes sense, right? Northing is just how far you are north of the equator. Easting, on the other hand, right, if you think about it logically, what we've done is we've actually created an origin where the equator and the standard line meet. And so you might think this would be a logical 0, 0, right? You'd actually be wrong. This is not what we call 0, 0. This is where things get a little bit confusing. All right, what we've done is we've actually add 500,000, right? So the easting is the distance from standard line plus 500,000 meters, right? And so this plus 500,000 meters is why we call this a false easting, right? Whenever you see it in any sort of software, you'll see it referred to as an X or an easting. That's because there are other coordinate systems and everything is X or easting. But in UTM specifically, what you actually have is called a false easting. And that's the reason it's called false is because we've added this 500,000 meters from the standard line, right? So let's just say, for example, we were here, right? So from the central meridian, right? Let's just say that this distance was 100,000 meters, right? We are east of the standard line, or sorry, we're west of the standard line. I am not doing good with my basic geography today, right? We are west of the standard line. Right? Just like we said with the prime meridian, when we were talking about the basic case of generating coordinates, right? When you're west of something, you're negative, right? So the true easting of this, in the sense of measured from the standard line, would be negative 100,000 meters, right? But because we add the 500,000 meters, the actual easting of this example would be 500,000 plus negative, because we're west of the standard line, 100,000, right? Meaning our actual false easting is going to be, actually, let me make sure that our false easting is going to be, right, 400,000. Okay. Hopefully that makes sense. The reason this is called a easting is because we're measuring east to west direction, and all coordinate systems, projected coordinate systems, are going to have an x and a y, or an easting and a northing. With UTM specifically, we call it an easting because that's the generic term. What's actually being reported is a false easting, because we're adding this 500,000 to prevent negative numbers, right? I'm going to make a note of this again, right? We add 500,000 to each easting to prevent negative numbers. Right. So let me repeat that one more time. When we measure distances in UTM for the coordinates, the value that we're being reported is typically referred to as an easting. But in UTM specifically, we add 500,000 to whatever easting value we get to prevent negatives. So in this example, right, we are 1,000 meters west of the standard line of the central meridian. But because we add the 500,000, the easting that would be reported is 400,000, not negative 100,000. Okay? Hopefully that makes sense. And as always, if you have any questions, please reach out. Thank you.